Hello. In this recording I'm going to discuss the role of two classic experiments, the Einstein-Haas effect and the Zeeman effect, and show how they lead to an understanding of the link between angular momentum, magnetism and atomic theory. Let's suppose we're considering an atom, for example a hydrogen atom, in which the negatively charged electron orbits around the central proton. And this orbiting motion has angular momentum, and the angular momentum quantum number is called L. And the atomic orbitals, which are the solutions of the Schrödinger equation, depend on three quantum numbers called n, l and ml. And in fact they're given by the products of two functions. A radial function which depends on the quantum number n and l, so this depends on the distance of the electron from the nucleus, and an angular function which depends on the quantum numbers l and ml, and this depends on the polar angles defining the orientation of the electron in space with respect to the proton. And we've seen already that these angular functions, they're called the spherical harmonics, and they're equal to the eigenstates of the angular momentum operators. So we're going to write them as ket L ml. So the eigenstates of the z component of angular momentum with eigenvalue h bar ml. Now what we see here in the hydrogen atom is that we have the electron executing a circulating motion around the proton, and it's known from elementary physics that the circulation of a charge generates a magnetic field. So there should be a link between the angular momentum with magnetism, and that effect was demonstrated very clearly by an experiment which is now known as the Einstein-Haas effect, which was first demonstrated in 1915. And the effect is as follows: that one designs an apparatus in which one has a cylinder of magnetic material, so for example iron, suspended by a thread. And around this iron cylinder which is suspended, one has a coil of wire. And the experiment is as follows: one passes a current through the coil, the current generates a magnetic field, and that magnetizes the material. And as the iron magnetizes, the observation is that the cylinder starts rotating. Now the rotation of an object is associated with angular momentum, so this experiment demonstrates a link between angular momentum and magnetism. So let's suppose we have a magnetic object, like a bar magnet with a north and south pole. If we're doing classical physics, we associate this with a magnetic dipole, which defines its interaction with a magnetic field. So this is a vector, so we could describe it using three numbers, which define its magnitude and direction. And suppose that magnetic dipole interacts with a magnetic field, which is also a vector. In classical physics, the energy of interaction between the magnetic dipole and the field is given by minus the dot product of the magnetic dipole and the magnetic field. So this can be written as the product of the x, y and z components multiplied in pairs and then added together. And it can also be written as the magnitude of the magnetic moment multiplied by the magnitude of the magnetic field multiplied by the cosine of the angle between them. Because of the minus sign, the energy is minimized when theta goes to 0, and that's the principle of the compass. The compass aligns itself, minimizing the magnetic energy when the magnetic dipole is aligned along the magnetic field. Now in quantum mechanics we simply replace these quantities by operators. So instead of the magnetic dipole vector, we have the magnetic dipole operator, which is a vector operator, meaning that it has three components, each of one is an operator. And instead of the energy, we have the magnetic Hamiltonian for the interaction between the magnetic dipole and the magnetic field, which is given by the product of the x operator for the magnetic dipole and the x component of the field, and the same for the other two components. Now suppose that we choose to put the magnetic field along the z-axis, then we write simply that the magnetic field is given by a vector with three components, but only the z component is finite, and then this expression simplifies to minus mu z b, where b is the magnetic field along the z-axis. Now the Einstein-de Haas effect tells us that there's a link between the angular momentum and the magnetic moment. So we can write the operator for the magnetic moment as simply being proportional to the operator for the angular momentum. So that's the magnetism and angular momentum link. And the proportionality constant gamma here, this is called the magneto-gyric ratio, although sometimes it's called the gyromagnetic ratio. Those two ways of describing it are actually referring to the same thing. Hence, the magnetic Hamiltonian for a quantum system is given by minus the magnetic moment operator and the magnetic field, assumed to be along the z-axis, and that's given by gamma, the gyromagnetic ratio or magneto-gyric ratio, multiplied by the angular momentum operator along the z-axis. And that has a consequence that the angular momentum eigenfunctions ket L ml are also eigenfunctions of the magnetic energy, with eigenvalues which depend on the value of ml, the magnetic quantum number. And those eigenvalues are simply given by minus h bar gamma b ml. Hence, since ml only takes a restricted number of values, depending on the angular momentum quantum number L, hence the energy only takes a certain number of values. Hence, if we plot the energy of the system against magnetic field, then the energy levels split into a number of states depending on the value of L. So this case would be for L equals 1, and then we have 3 levels with ML is +1, 0 and -1. And similarly for L is 2 we would split into 5 levels. In general, the energy of the system splits into 2L+1 levels depending on the size of the magnetic field. As the field increases, the splitting increases, and that's called the Zeeman effect. This shows actually the original observations by Zeeman in around 1896, which show the splitting of spectral lines by the application of a magnetic field. And the Zeeman effect is used, for example, to estimate the magnitude of magnetic fields of celestial objects like the surface of the Sun. So we've seen how the Einstein-de Haas effect and the Zeeman effect establish that there's a link between angular momentum and magnetism, and that the quantization of angular momentum is revealed as the quantization of magnetic energy levels. In the next lecture we'll look at the phenomenon of spin.